Hello everyone, I'm Yihao from the Johns Hopkins University. In this presentation, I'm going to introduce our new framework for deformable image registration. The purpose of deformable image registration is to establish a nonlinear spatial transformation between a fixed and a moving image. Applying this transformation to the moving image will produce a warped image that is spatially aligned with the fixed image. For example, given the fixed and moving image on the left, the spatial transformation on the right will warp the moving image to make it align with the fixed image. There are many traditional registration algorithms exist based on maximizing similarity between the fixed and moving images. Recently, deep learning has also been used for deformable image registration. Compared with other tasks, learning registration does not always require ground truth. For example, when the ground truth displacement field is available, we can adopt the common supervised training approach. Once the network is trained, it can produce displacement field D for unseen fixed and moving image pairs. Therefore, it is much faster to use than most of the traditional methods. When ground truth is not available, we can use the moving image and the output of the network to produce the warped image. And then we can compute the dissimilarity between the fixed and the warped image and use it to update the network parameters. Our proposed method that we will introduce can be trained with or without ground truth. For this presentation, we will focus on the unsupervised training as an example. So let's look at it in more detail. Firstly, many of the existing work interpret the output of the network as displacement fields. It is commonly visualized as a vector field. At every voxel location, it stores another location that the current voxel corresponds to, in the form of relative spatial offset. Therefore, the displacement field represents coordinate correspondences between the fixed and the moving image. Alternatively, we can represent the same coordinate correspondence using the absolute spatial coordinates. We call this the sampling grid representation. Let's define the identity grid as a map of coordinate for every voxel location. Using the identity grid, we can easily convert the relative spatial offset to absolute spatial coordinates for the equation provided here. To produce the warped image, we can use a grid sampler. A grid sampler uses a sampling grid G and the moving image to produce the warped image. You can imagine this process as rearranging the voxel in the moving image without changing its original intensities. The new order of the voxel is specified by the sampling grid. From the above discussion, you may already notice that the learning registration is different from other applications of neural network in medical image analysis. It has been shown that networks are very good at extracting features, but in registration, in addition to feature extracting, we need to compare two images, and more importantly, the output have a very specific meaning. That is, it is a coordinate correspondence. Imagine that we have already extracted good features from the fixed and moving images, and from those features, we find the best match for each voxel. Ideally, at this stage, we just need to output the coordinate of the best match. But we observe that all the current method relies on network to learn to do this straightforward task, because there is no existing network structure that is differentiable and can produce a coordinate by comparing two images or two feature maps. However, learning those tasks will put extra burden on the deep learning methods, and people have found that the performance of a UNet is only similar to the traditional method, but not better. There are mainly two directions people are exploring to boost the deep learning method performance. The first is to introduce a correlation operator to explicitly compare the fixed and moving images. Several works also use the transformer instead of a convolutional neural network. The transformer is a network structure based on attention module. It takes three inputs denoted as query, key, and value, and its output is computed through a sequence of matrix multiplication and softmax operation. The first contribution of this work is proposed a module named Coordinate Translator. It is a differentiable layer that is designed for doing two tasks. When given two feature maps, F and M, extracted from the fixed and moving images, the Coordinate Translator will first match the features between F and M, and then the matching result will be directly translated to coordinate correspondence. Therefore, the output of the Coordinate Translator is a sampling grid that can be used by the grid sampler to warp the moving image. But how this is different from existing works that use a convolutional layer or a fully connected layer to output a displacement field? The answer is that there is no learnable parameter in Coordinate Translator. So it is a fixed operation, and the coordinate it outputs is only dependent on the similarity of extracted features in the two feature maps. But why this is useful? The answer is that in registration, we already know that we need to match features in two images, and we also want to output the coordinates from the matching results. This straightforward logic has been used in many traditional registration algorithms, but because deep learning methods require every computation to be differentiable, it has to use a trainable network to learn this simple logic. Coordinate Translator handles this known procedure with fixed but differential operation. It is more accurate and allows the trainable part of the network to focus on feature extracting. In the bottom figure, only the feature extractor has learnable parameters. To correctly register two images, we only need the feature extractor to produce similar features for the same anatomy in the two images without worrying about the coordinates of the image. In this slide, I will explain how exactly the Coordinate Translator works. Let's start from the attention module we showed earlier for the transformer, but instead of a query and a key for the first two inputs, consider use the feature map F and M from the fixed and moving image. We realize that the first matrix multiplication in the attention is actually calculating a correlation between every voxel in F and every voxel in M, and its output can be interpreted as a matching score for every pair of voxel. In many cases, the fixed and moving image are already roughly aligned, for example, by a affine transformation. So for a given voxel location X, shown in the fixed image on the top, we only need to compare it with voxels in its neighborhood area. And we can still using a matrix multiplication for this calculation by removing certain elements from the matrix M. The matching score is then converted to the matching probability using the softmax operator. For the example given on the right, it is likely that inside the search area of neighborhood around X, the yellow voxel in the moving image will have the highest matching probability. The last step is to translate the matching probability to coordinate correspondence. We accomplish this by a weighted sum of all coordinates inside the search area. The weighting is determined by the matching probability from the previous step, so if the yellow voxel have the highest matching probability, the output coordinate will be pulled closer to the coordinate of the yellow voxel. This last step can be implemented very easily also using a matrix multiplication with the identity grid as one of the input. We can see that Coordinate Translator takes the form of an attention module, but with carefully designed input, it translates two feature maps into a sampling grid based on feature similarities. We have been assuming that a feature extractor has been well trained to produce meaningful feature for the Coordinate Translator to use, but in practice, the network weights are initialized randomly so that the initial output of Coordinate Translator is a random sampling grid. We find that such initialization makes the network more difficult to train. Therefore, we introduce a positional encoding layer to force the initial output of the Coordinate Translator to be the identity grid, and thus the initial warped image to be the moving image. We accomplish this by adding position information to the feature maps. The idea is that during the initial training stage, the Coordinate Translator will find the best match based on the position of the voxel instead of the feature that extracted from an encoder network. The same position in the fixed and moving image will produce the best match and thus outputting the identity grid as the initial output. The position information we added to the feature map is given by the following equation. For 3D images, it is a 6-channel feature maps calculated based on the location of each voxel. The location on each dimension is mapped to 2 values representing a unit vector between 0 to pi. The reason we choose this way to encode the position information is that when taking the inner product or correlation of this positional embedding between 2 locations x1, x2, the result is determined by the L1 distance between the 2 locations. We initialize the feature extractor to output a 0 feature maps and then add this positional embedding. Therefore, the matching score calculated in the coordinate translator will achieve maxima when the 2 locations are the same. Based on the coordinate translator, we propose a multi-scale network named M2Grid for deformable image registration. M2Grid follows the commonly used coarse-to-fine strategy. It will first register downsampled version of the fixed and moving feature maps, and after applying the coarse transformation to the moving feature maps, bring it closer to the fixed image, it will then estimate a more detailed transformation at a finer scale. From the fixed and moving image shown on the left, we use an encoder network that is similar to the encoder used in UNet to extract multi-scale feature maps from both images individually. Then we start from the feature maps with the lowest resolution and use a coordinate translator to produce a sampling grid. This coarse sampling grid is then used to warp the moving feature maps at finer scale and produce a second and more detailed sampling grid. This process repeats until we reach the original scale of the image, and when we use the 5-level network, the multi-scale strategy produces 5 sampling grids at different scale. All the sampling grids are composed to produce the final sampling grid G, and the composition is implemented also using the grid sampler. We can visualize the effect of the sampling grid at each scale by warping the moving image with those intermediate sampling grids. Here we show the moving image on the left and the fixed image on the right. The 5 images in the middle, from left to right, show the effect of the 5 sampling grids. Because the fixed and moving images are rigidly registered as a preprocessing step, the difference after applying G5 is not obvious, except maybe at the right boundary of the brain. But as we move to the finer scale and compose more detailed sampling grids, we can see how the moving image is warped towards the fixed image. From the final result, although there are some tiny differences, we can see that it is very similar to the fixed image. Here we provide some visual comparison between M2Grid and several traditional and deep learning-based methods. The goal is inter-subject registration of T1 weighted brain MR images. The moving image is shown on the left column and the fixed image is shown on the right column. The 2 rows are 2 examples from different subjects. We provide the result for 2 versions of our method. The M2Grid Lite is a version that skips the final scale so it can be trained faster with smaller memory consumption. From those 2 examples, we can see that our method produces visually pleasing result that looks more similar to the fixed image. Here we show the quantitative result on inter-subject registration of T1 weighted brain MR images. Scans from 2 public available datasets, OASIS 3 and IACL, are preprocessed and used in our experiment. Because we don't have access to ground truth displacement field, we use an alternative approach to evaluate the accuracy of the results. Specifically, all scans are first segmented using a whole brain segmentation algorithm called SLANT. The output labels are combined into 9 labels follow a previous paper. For all methods in our experiment, a deformable transformation is produced from the intensity image and applied to the label image. Ideally, the warped label image should also align with the fixed label image. Therefore, we calculate the dice coefficient between the 2 label images. We compared our method against several deep learning and non-deep learning methods. It can be seen in the table that the dice coefficient for our method is much better than the comparison method. In addition to the dice coefficient, we also report the number and percentage of voxel with negative Jacobian determinant. From this table, we can see that our method achieves much better dice coefficient with a low number of non-diffeomorphic voxels. We also evaluate our method using the Learn-to-Reg challenge dataset. The results are evaluated also using the fixed and warped label image, but with 35 labels. The first, second, and last column in the table show average dice coefficient for all 35 labels, 30% lowest dice coefficient of all cases, and the 95th percentile of Hansdorff distance. In addition, the standard deviation of the log Jacobian determinant is reported to measure the smoothness of the transformation. This result also shows that with only a UNet encoder, IM2Grid achieved top performance against the recent published traditional methods and deep learning methods with much complicated structures. I would like to thank my co-authors, collaborators, and the funding source for the contribution and support. Thanks everyone for your attention, and please feel free to contact me if you have any questions.